Okay, can you see my screen and can you hear me well? Hello guys, can you hear me well?
Yeah, I can hear you.
Okay, great. Yeah, it's just odd that nobody's responding or nobody's sending some messages via the chat. All right, so let's first look at the basic graphs for the polar coordinate for polar curves. Um, I was actually looking for a cheat sheet for these graphs. That's a little. That's one reason why the holdup. I was trying to browse some polar curves cheat sheet on the net, and I was supposed to paste it on our worksheet. But all right, let's see if there are some good ones here that I can copy paste. Let me see. Okay, there we go. I don't know if it's high definition. Okay, it's kind of blurry, so let me do it manually. So we have the following simple graphs in polar coordinates. Basically, you can deduce the type of graph that you have by converting your polar equations into the Cartesian coordinates. But as you might have seen last time, it will take some time to convert a polar equation into a Cartesian equation or a rectangular equation. And even until then, we need to manipulate the equation algebraically just to write it in the forms that we know from pre-calculus. So well, it will be helpful if you will know the following right away. So first, the graph of simple circles. The most basic circle is r equals a. A is a constant. So this is just the circle centered at the pole. So this is circle centered at the pole. And then we have r equals a sine theta. This is a circle which is primarily on the y-axis, and then you have r equals a cosine theta, which is a circle that is primarily on the x-axis. I easily remember that because remember that I told you last time that sine is always associated with the with the y-axis or the y variable, and cosine is always associated with the x variable. Right. Now, some other basic graphs. We also have theta equals k, which is a diagonal line, or this is not necessarily diagonal, but it is a line through the pole. You can think of it as the angular line. So theta could be equal to pi over 4, theta equals pi over 3. So these are rays in your Cartesian coordinate system. And we also have r equals theta, which is an Archimedean spiral. Okay. And then did I forget some of the basic ones? Then I guess after this we can go to the limaisons. The limaisons are from now on I'll just write this as a usual C. So it's a limaison. It will take the form either r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta. And depending on the ratio between A and B, we will know exactly how these limaisons look like. So if the ratio A over B is less than 1, we have a limaison with a loop. If A over B equals 1, we have a cardioid or a heart-shaped graph. If A over B is between 1 and 2 exclusive, then this is a dimpled limaison. Or some books call it a limaison with a dent. And then if A over B is greater than 2, we get a convex limason. Okay. Maybe let me see if I can find a good picture of limasons here. Let's see if this one's good. All right, probably this will do, but it only has 2 limasons here. Let's see. Okay, I think this is good. Okay, so basically, these are how these limasons look like. So it's a limason. When A over B is less than 1, you have a limason with a loop. If A over B is equal to 1, you have a cardioid. If A over B is between 1 and 2, you have a dimpled limason. And they don't have a convex limason that happens when A over B is greater than 2. So you can think of it as the smaller the value of A over B is, um, the more you poke one part of the limason so that it will go inside. So the smallest one is A over B is less than 1. So that's like poking one side of a circle by a lot of force that caused the part of the limason to go inside, right? So that's what you got. If A over B is equal to 1, we are just poking one part of a circle by just enough force to draw a heart-shaped graph. If A over B is between 1 and 2, you're poking it with a little bit more force that causes it to have a dimple. And when A over B is greater than 2, then it is as if you are barely poking it. So you'll just get just a little deformation from a circle, right? I'll hope to find some more, some better picture for this next time. Now, there are also some graphs, the lemniscates, or other books call it propellers. Okay, these are they have the equation of the form r squared equals a sine 2 theta, or r squared equals a cosine 2 theta, which is easy to spot because among the polar curves that we will study, they are the only ones with an r squared on one side. So they look like this. They really look like propellers. Pardon the the uneven graphs, but basically, yeah, these are how lemniscates look like. That's why I would like to call them as as propellers instead of lemniscates. And then I guess the last type would be petals or roses. I look at the textbook and it seems they call it petals, but I used to call them roses. They have the equation of the form r equals a sine n theta, or r equals a cosine n theta, right? Where the value of n determines how many petals the rose will have. So if n is odd, then you will have n petals. I don't know, how did you call it in the lecture? They say n petals or n leaves, or I'm not sure. I forgot what is written in the textbook, but I usually call them roses with n petals. When n is even, you will have a rose of 2 n petals. So to streamline the presentation of sections 2.2 and 2.3, I will discuss sketching the graphs of these polar curves in conjunction with setting up the integral that will give us the area for some regions bounded by these polar curves. All right. Now I have worksheet number 22 uploaded just this morning, which covers or which has the exercises from section 10.3. But I'll try not to answer problems from 10.3 just to leave this exercises to you. So I have prepared some examples for us to discuss. But before going there, mhm. All right, so I see John has a question here. Probably, John, I can answer your question as we go along the examples for finding the areas of these polar curves, because finding the points of intersection for polar curves is very integral in setting up the area using integrals. So we will see that later. So just pay attention in the details of the solutions that we will do, probably examples 3 and onwards, because I would start with some more basic examples wherein we don't need points of intersections yet, but I'll rest assured that I'm going to go there in finding the points of intersection. All right, so let's consider some examples. So here what we do is we'll sketch the region described in each problem. Then set up the integral that will give their area, right? Will it be okay if we just set up the integral? Because evaluation is the thing of of previous chapters. But if there could be some examples wherein we we can compute the integrals, but that will take a little bit more time because oftentimes you will deal with very complicated trig equations. Not that complicated, but that will require us to use some identities along the way. So I can show you some few computation of the integrals, but I'll focus more on setting up the integrals. I hope that's okay with you guys. Oh, by the way, I forgot to recall here that maybe I'll put here. Recall for the areas in polar curves in polar coordinates, the general form is this. The area will be equal to 1/2 integral from an angle alpha to an angle beta of the radius squared d theta. So your radius, your r here could be dependent on theta. It could be a constant, but the thing is, we put a function inside. The integrand would be r squared, and don't forget the 1/2 outside. If your region is bounded by two curves, then the area could take this form. So it could be 1/2 from alpha to beta. You have your outer radius squared minus inner radius squared d theta, which is basically the same principle we used in previous chapters, wherein we set up the integral that will give us the area of curves of regions bounded by rectangular curves. This time we'll just work with rectangular with polar equations. And for the integral, don't forget some mainstays. We have the 1/2 outside for the area. And then your bounds would be angles because we will be integrating with respect to theta. And the integrand will either be a radius squared whenever your region is bounded by only one curve, or the difference of the squares of the outer radius and the inner radius. All right. So let's look at some examples first. Let's try. Okay, let's write this one. The region by r equals secant theta, and the raise theta equals pi over 2, and theta equals pi over 3. Okay. So as usual, it would be better to have a graph of the region to know exactly what is the outer radius, the inner radius, or if there's only one radius involved. So here, let's look at the equations. We have theta equals pi over 2 and theta equals pi over 3. We know that these are just lines passing through the pole, so they are easy. Perhaps let's start with r secant theta. Do you guys remember what is the graph of r equals secant theta? Have you encountered this before? Okay, if you forgot, you can just do a quick conversion. Remember that r equals secant theta can be written as r equals 1 over cosine theta, right? And then you multiply both sides by cosine theta, we get r cosine theta equals 1. And from our conversions, r cosine theta is just x. So we just have x equals 1. So the graph of r equals secant theta is simply a vertical line through x equals 1. Mind you, recall that the graphs of a polar equation and its rectangular coordinate, its rectangular equivalent are essentially the same. Be it you plot it on the rectangular or on the polar plane. So if I will draw the graph here. Okay. Let me just copy this so I don't have to draw the axis over and over again. So this is just x equals 1. So let's put x equals 1 here. Oops. There we go. So this is the graph of r equals secant theta, right? And then we want to integrate or to find the area of the region bounded also by the rays theta equals pi over 2 and theta equals pi over 3. Theta equals pi over 3 could be somewhere here. It's just a half ray because that will just go for theta equals pi over 3. And the other one is theta equals pi over 2. Oh, but this would be an infinite line. Perhaps, let me see. Perhaps I had a typo here. It shouldn't be pi over 2 because if it was pi over 2, then it would be unbounded all over there, right? Because this is theta equals pi over 2. So let me change that a bit. Let me make it, I think this should be pi over 6. Yeah, that's what happens when I invent problems on the fly. So pi over 6 and pi over 3. So pi over 6 could be somewhere here. So that makes the shaded region this one, or the region we are interested in is that yellow region. All right. So that's the region. And now let's set up the integral that will give us the area. Remember that the area is or has a mainstay 1/2 integral with respect to theta of the radius. Well, how do you find the radius? Well, what I do is to draw a ray and imagine this ray traveling, being rotated along the polar plane. So this guy is being scanned that way, right? But I will stay on the shaded region. So the starting point for this radial ray will be from here, and then it will travel until here. So the angular span of that sector that is traveled by that radial line that I just drew would be from theta equals pi over 6 until theta equals pi over 3, because that is the angular span of the region of interest, right? And then now, what would be the integrand? The integrand would be the radius. Well, if you look at my green ray here, which is what I use to measure the radius, the radius always starts at the pole and will stop here, right? If that if my ray, if the green ray is over here, then the starting would be the pole and it will end up at the vertical line. And imagine the green ray being being transported between pi over 6 and pi over 4. You will know that the radius will always lie on the vertical line. That's why I know that from pi over 6 to pi over 3, I should integrate r equals secant theta, right? So that's why I know that here my integrand would be secant theta. But remember, we're doing the integration in polar coordinates. You have the radius squared inside your integral. Okay? And I guess this is not hard to evaluate because what we can do is we know the integral for secant, so that's going to be tangent theta evaluated from pi over 6 to pi over 3, right? So this would be 1/2 times tangent pi over 3 minus tangent of pi over 6. So this guy would be 1/2. Tangent of pi over 3 is root 3 minus tangent of pi over 6. That's going to be 1 over root 3. Is that correct? Kindly double check my trigonometric values here. I guess that's right. So if I simplify, so this would be just 1/2. I'll have 3 minus 1 over root 3. So this will be 1 over 2, 2 over root 3. So this will be 1 over root 3 or root 3 over 3, right? I forgot that the instruction is just to set up the integral that will give us the area, but I tried to show off a little bit here and computed the integral. So this would be root 3 over 3. All right. Any questions with that? Is that fine? Okay. All right, let's try another one. Let me see. This is a common problem that I see in exams or quizzes. Find the area of the inner loop of r equals 1 minus 2 cosine theta, right? So for this one, we need to sketch the graph first, really, of 1 minus 2 cosine theta and find how it looks like. But here I know that the graph of r equals 1 minus 2 cosine theta is a limmason. And here a over b is equal to 1 over 2, which is less than 1. So we have a limmason with a loop. So in sketching graphs of limmasons, it would be great if you have an idea of how the limmason should look like. So here I identified that I have a limmason with a loop by looking at the ratio of a over a and b. So why is it important? Because we cannot afford to compute lots of r values for lots of theta values just to get the shape of the graph. So I will rely on some special values for theta to give me the r value and a knowledge of the supposed final product for the graph, or the final look of the graph. So for sketching limmasons, what you can do is to make a table of r and theta values. Okay, and what we will use would be the quadrantal values for theta, or the quadrantal angles. So you start at 0, then pi over 2, pi, 3 pi over 2, and 2 pi, right? These are the only angular values that you will need. And then plug these values into the equation of the limmason, right? So when when theta is 0, I'll get cosine of 0 is 1, so 1 minus 2, so that's going to be -1, okay? When when theta is pi over 2, this would be 0, so we'll have 1. When theta is pi, this would be -1 times -2, that's going to be 2. 1 plus 2, so it's going to be 3. Theta is 3 pi over 2. This means this guy will be 0, so we'll get 1. And then when theta is 2 pi, I'll get the same value as what I got with 0. Okay? So these are the 5 values that actually you can reduce it to simply 4 because we know that the value at 0 will be the same value as 2 pi, right? So let's see. Let's sketch the graph. Okay. So here, I will need the 2 concentric circles. Perhaps I'll delete these and draw another line here. Okay, so I need 2 concentric circles just to guide me in plotting radii. So I need the 2 concentric circles, one with radius 3 and one with radius 1. So I'll just draw them here. I'll use this. So this is radius 1, and this would be radius 3, for instance. Okay. So when theta is 0, okay, when theta is 0, the radius should be -1. So this is your theta equals 0, right? But since the value of r is -1, I will not plot at this point or at this ray, but I will plot in the opposite direction. So I'm going to go 1 unit in the opposite direction. So that will give me the first point here. So this is the point -1, 0, the polar point -1, 0. All right. And then when theta is pi over 2, so we are supposed to travel here. The r value is 1, so I will put my point 1 unit in that direction. So I get this. All right. When r is equal to when theta is equal to pi, so we'll be here, right? The r value should be equal to 3. So that means in that direction, I will have this point. Okay. And then when theta is 3 pi over 2, so I am at this direction, I will plot 1 unit along this ray. So 1 unit, I'll go in the smaller circle. And when theta is equal to 2 pi, I'll get back at here, right? So, but I know that I'm expecting a limason with a loop. So basically, this will look like this. So you'll start here. Oops. Yeah. Oops. Sorry. Yeah. This is one of the topics I hate the most because I need to draw a lot of things. So, oops, what's happening? Okay, there we go. So I'll start here. So I know there should be a loop somewhere there. And then the graph will look like this. Okay, so that's your limason with a loop, and we're looking for the area of the region inside the inner loop. So that means that guy, right? So we're looking for that area. Okay. So the thing here is we will be looking at what is the angular span within this region, right? So what do we know? Well, we know that one of the loops will start here when r is -1, and that started when theta is equal to 0, right? So when theta is equal to 0, we are here. And then if you want to trace it properly, the graphing of this looks like this. So go here all the way there. Or is it the other way around? Hold on. because there should have been an order to this. Okay. Oh, there we go. So the right tracing for the plotting of this limason, if you'll go from increasing theta, you'll start here, you'll go around here, then you'll go there, and then that's how it will go in increasing theta values. So, but we need to find when is the starting point for the loop and when is the ending part of the loop, right? So the loop started here. The inner loop started here, but we know that happened when theta equals 0. And then it will go here, it will exit a little bit, and it will exit when r is equal to 0, when you hit the pole, right? But if you integrate along that region, we will be only getting half of the area. Maybe I should enlarge that. So, okay, there we go, right? Again, we start at theta equals 0 here. And then as theta increases, we will go here, and then we will hit the pole, right? And the pole is the only point on the plane when r is equal to 0. But when we integrate from this theta value until the theta value when r is equal to 0, we will just be getting half of the inner loop, right? But that's fine because I can just multiply whatever area I get from here by 2 to get the area of the other half of the loop, right? Or to get the area of the entire loop. Because if I will do this in one integration, I will need to be careful because from theta equals 0 until this theta value, I am on the inner loop. But right after this point, I will be on the outside loop. And I will re-enter the loop only when I hit r equals 0 again. And then it will end up at 2 pi, right? So, but I hope it's clear that we start at the loop we can look at the loop starting at theta equals 0, and then let's look for what is the theta value when we will first exit the loop, right? And that will happen when r is equal to 0. So note, we will exit the loop when r is equal to 0, right? Again, that is because you're starting here at r equals 0. As r increases little by little, you'll go here, and at some point you will hit the pole, and that will signal the exit from the smaller loop, right? From the inner loop. So r is equal to 0 when, for what value of theta? Well, we'll just plug in r equals 0 into this equation. So we'll get, so we solve for theta, for such theta. We get 0 equals 1 minus 2 cosine theta, right? Or we can say this is 2 cosine theta equals 1. Or that means cosine theta equals 1/2. What is the angle when cosine is equal to 1/2? Cosine will be 1/2 when theta equals pi over 3 on the first quadrant. And the other one would be at, when will it be 1/2 again? 5 pi over 3. Right? So this tells us the limason, or the way the limason was drawn, was like this. Theta equals 0, theta increases, but when theta is equal to pi over 3, we are at the pole because at theta equals pi over 3, r is equal to 0. And then past pi over 3 will travel along the outer loop, travel some more, but when theta equals 5 pi over 3, we are at the pole again, so we will re-enter the loop, and then it will close at theta equals pi over 2, all right? But it will be hard to integrate it twice, because you can integrate from 0 until pi over 3, but you'll just get half. And then to get the other half, you can integrate from 5 pi over 3 until 2 pi, right? But that will require you to evaluate two integrals. You can take advantage of symmetry instead. Note that this guy is symmetric with this part of the loop. So I can just take one of those integrals and multiply the result by 2, all right? So that means the area of the shaded region would be twice the area of 1/2 of that loop. But the area always has a mainstay 1/2, integral from 0 until pi over 3. Again, because the loop started at at 0, and half of the loop will end at pi over 3 when we will exit the inner loop. That's why I'm performing the integration there. And then the radius, if you draw the radial line there, or the radial ray, the radius is always on the limason. And the equation of the limason is 1 minus 2 cosine theta. But remember, the integrands for polar areas has a square in it, d theta. Okay, and so that will be the area of the inner loop. All right, any questions? You guys are uncharacteristically quiet today. I hope I'm making sense here.
Yeah, it's working out. I get it.
Okay, great. Yeah, so let's try another one, perhaps related to John's question, a little bit related, though I'll use probably different functions. But this will entail finding the points of intersection, especially if you have two curves involved. So let's try problem 3. Let's find the region outside r equals 2 plus 2 sine theta, but inside r equals 6 sine theta. Okay. Now let's sketch the region. So the first graph is first equation is that of a limason, right? Is that of a limason, right? And since a over b will be equal to 1, right? That's going to be 2 over 2. So this means we have a cardioid. So it's a cardioid or a heart-shaped graph, right? Meanwhile, second equation is that of a circle, right? So let's sketch their graphs here. Okay. Now let's start with the limason. We have, let me use a different color for the graph. Let's use this, yeah. So for the limason, again, the key is to find the R values for the quadrantal angles. So it starts at 0, pi over 2, pi, 3 pi over 2. I'll just include 2 pi out of habit. And then we plug in 0. You plug in 0 to this theta. This guy will be 0, so the radius would be 2. All right. When theta is pi over 2, this is 1, so we'll get 4. When theta is pi, this is again 0, then plus 2, so we'll have a 2 there. At 3 pi over 2, this will be what? 3 pi over 2, this would be negative 1, so we'll have a negative 2 plus 2, so we'll get a 0. And at 2 pi, we'll get 2 again. All right. So this signals I need two concentric circles, 2 and 4 of radius 2 and 4. So let me say this is my circle of radius 2, and this is my circle of radius 4. Just to guide me for plotting the radial components. All right. Now let's plot the points. When theta is 0, so we are here at theta equals 0 ray, r is equal to 2. So I'll put the point here. That's my first point. The second point would be at theta equals pi over 2. We're here, and we need to travel 4 units along this ray. So I'll go on the larger circle. At pi, which is here, I need to travel 2 units because r equals 2. So the point will be on the smaller circle. And then when the theta is 3 pi over 2, we're here. So that means r is 0. We'll be here. And then we'll be back here after at the theta equals 2 pi. So basically the graph will look like this. So it's a heart-shaped graph. but make it more rounded. It's a rounded heart-shaped graph, so it will look like that. Okay. All right. And then the next one, for the circle is actually a circle tangent at the pole. So this is r equals 6 sine 2 theta. It will, I know that it is tangent to the pole. So whenever you have a circle of equation a sine theta or a cosine theta, so the pole is a point in it, right? It would be tangent there. You have a sine function there, so it's gonna be either a circle over here, lying on the y-axis, or below the on the negative y-axis, because I have a sine, right? And the diameter of the circle would be 6. So the diameter is 6. So basically, what we get here would be a circle something like this, right? Because the diameter, which is this guy, should be 6 units. So it's a circle tangent to the pole lying on the positive y-axis of diameter 6. All right. Now let's see the shaded region. The shaded region is outside the limaçon, but inside the circle. So basically, this is what we're looking at. Because it is inside the circle, but outside the limaçon, right? Okay, so that's our shaded region. And for this, for the area, I need to do some integration, right? So we could do the integral of what? Well, we need to find the points of intersection because, you know, the region will start here. The region will start at this theta value. This is our theta equals alpha, which we don't know right now. And the ending theta value will be here. Theta equals beta, which we don't know right now. All right, because the region will start there. And then you can draw your radius. Your radius will be a ray that will travel this way until you go to that point of intersection, right? Again, alpha and beta will be determined by the points of intersection here and over there. So we need to solve for the points of intersection. Now we need to solve for the POIs. Because again, I know that the region or the shaded region will start at the point of intersection and will end at the other point of intersection. So let's solve for them. Now we solve the points of intersection by putting the two equations equal to each other. The limaçon has r equals 2 plus 2 sine theta. The circle has r equals 6 sine theta. Both are equal to r, so I can equate the two right-hand sides together. So I will have 2 plus 2 sine theta equals 6 sine theta, right? So I need to solve this equation in order to get the points of intersection. This will give me the theta values at which the two graphs will intersect. And essentially, I only need the theta values because that will signal the starting and end of my integral, the starting and ending point of my integral, right? So that's why I hope you still remember how to solve trigonometric equations. So here what I can do first is to isolate the trig function to one side. So basically, I'll transfer it to the right side. So I'll have 2 equals 4 sine theta. And then divide both sides by 4. So I'll have 1/2 equals sine theta. And then I'll go back at the unit circle. What are the thetas whose sine is equal to 1/2? Sine will be equal to 1/2. Theta equals pi over 6. And 5 pi over 6. Right? So that means this intersection over here occurs when theta equals pi over 6. And the other intersection will be here at theta equals 5 pi over 6. So that means the region will start here. This is theta equals pi over 6. And then we will travel until we reach theta equals 5 pi over 6. So that means our integral would be, just write the solution here. So the area, there's a mainstay 1/2 integral from your starting angle, which is pi over 6, and ending angle 5 pi over 6. And then what is the radius? Well, to find the radius or the integrand, what you can do is to draw a ray passing through a nice portion of the region, right? And you notice here that the outer radius will be determined by the blue curve, and the inner radius will be determined by the red curve, right? And that is uniform across all theta values, because even if your radial line is over here, your outer radius is still the blue curve, and your inner radius is still the red curve. So no need to split the integral up into pieces, right? So you'll just follow the formula. So it's going to be outer radius, but the outer radius would be determined by the circle 6 sine theta quantity squared minus the inner radius 2 plus 2 sine theta quantity squared, all multiplied by theta. Let me just move it here to make some room for my d theta. Okay, d theta, all right? Or you could take advantage of symmetry, or you can say this is twice the area from pi over 6 until pi over 2 of 6 sine theta quantity squared minus 2 plus 2 sine theta quantity squared d theta. Here I'm taking advantage of the fact that I know that the region will be symmetric with respect to theta equals pi over 2, right? So I can simply afford to integrate from pi over 6 all the way until pi over 2. I'll get the area of this region. Just multiply that area by 2. I'll get the area of the entire region. Okay? So, oh, it's already time, but do you guys have questions? I hope this will help you, John, with your problem there. One thing I didn't do is to find the remaining points, right? So if you're looking for really the points of intersection, because here all I needed are the theta values of the POIs. But if you need to get the R value for the POIs to give you the complete coordinates for the points of intersection, all you need to do is to plug in the thetas that you computed here to either of the two equations to give you R. So if I want R to be equal to find R at the points of intersection, I'll get my first theta, which is pi over 6. Plug in pi over 6 here, you get the corresponding R value. Or you can also plug pi over 6 over here. It doesn't matter which of those two equations you will plug the theta components into, you will get the same R, right? So you can pick the plug in here because it looks simpler. All right. Morel is asking if I'll be available after classes or and during finals week. Yes, Morel. I still have my CASA tutorials until the close of the session. Until the official close of the semester. That means after the finals week. So my usual schedule at CASA is from 6 to 7 PTH. But if you are not available then, and if you want to meet with me, just kindly send me a message, and probably we can schedule something up as an office hours. All right. But I'll have to clear it up with Dr. Almus if we are allowed to do one-on-one consultations with students. But I think that should be fine. So just hit me up with an email or a chat via Teams so we can schedule a meeting. But generally, I'm free 6 to 7 Tuesdays and Thursdays, all the way until the official close of the semester. All right, guys. All right, sure, John. So you guys can, if you have classes, you can leave the room. I'll probably just help John with a couple of minutes with this problem. Let me see what seems to be the problem here. Okay, because your equations are a little bit messier than what we had. So you have r equals 9 sine 2 theta, and you have r equals 9 sine theta. I see the difficulty here. So here you equate the two r's together, so that means 9 sine 2 theta will be equal to 9 sine theta. Okay, and then you can cancel the 9's. But here you cannot isolate the trig function to one side of the equation, right? So that signals the need for the use of identities. You can go back to your trigonometry notes, and look for an identity for sine 2 theta. I bet you will find 2 sine theta cosine theta, the double angle identity for sine, equals sine theta. And then here you can collect all trig functions to one side, because ultimately your goal is to isolate the trig function to one side. So I want one side to be a constant as much as possible. And look at the left-hand side here. I can factor out a sine theta. So I'll have 2 cosine theta minus 1 equals 0. So the POIs would be those thetas, or those with thetas such that sine theta equals 0, or 2 cosine theta minus 1 equals 0. So here we'll see that cosine theta should be equal to 1/2, and here it's sine theta equals 0. All right. Then you will find that here theta will be equal to 0 and pi. Here you'll get theta equals what? This would be pi over 3 and 5 pi over 3. Okay. Does that clear things up, John? So that's a signal that you need to remember, or to go back to your trigonometry notes to look at some techniques in solving trig equations.
Okay, thank you.
All right, you're welcome. All right, bye guys. See you on Friday.